By the time he warms up, I always down. Alright, so today we are on day 3 notes. So this is unit 5. Is it unit 5? Yes. Okay. Unit 5, day 3 notes. And again, some of this will be handwritten, some of it's going to be on paper that I give you. But for what we're writing today is linearization. Yeah, okay. Linearization. That's what it sounded like, but it looked weird. Linearization. What word do you notice within the word linearization? Linear. And inside linear is the word? Line. And here. Yes. Alright. Oh, I thought there was only one answer to that, but you guys came up with great answers. Alright, so we are going to be dealing with equation of a line. Woohoo! Now, linearization is also called linear approximation. Ooh. Thank you. I thought that was cool too. I mean, I didn't come up with that. Linear approximation. So just make sure you're familiar with both terms because it could be directly referred to on a question using either. Alright. So the idea with linearization is that we have an equation and we are asked to find a specific value that might not be so easy to do without a calculator. So what we do is we actually use the derivative and the tangent line of the value we do know to approximate the height of the value we don't know. So let's consider the equation just x squared. So let's consider f of x is x squared. It's a pretty simple graph. We know how to deal with that. And let's consider the point 2.134. Alright. Now, if I take 2.134 and I put it into x squared, could I figure out what that value actually is? Yeah, it's going to be quite a bit of work, particularly without a calculator. And when calculators revolt and take over the world, we can't trust them, and we need to be able to do this calculus without the calculator. So we could do it by hand, but it's going to take quite a bit of work. And this, honestly, is not too bad of an equation. What if I had, like, 5x to the 5th plus 3x squared minus 28x plus 104? That's going to be a lot to do by hand. So we use linear approximation, or linearization. I felt like I almost combined those together. Linearization. To get an approximate value of what the height is here. So if I were to try to find the function value, or the y value at this point, again, I can do it by hand, but it might not always be very easy to do by hand. So we're going to consider the tangent line to help us get an approximate idea for this. So what does this equal? Okay. So we're going to basically, again, create a tangent line with the point that we do know pretty well, that's close to it, to give us a good idea. So I don't easily know what this value is squared, but what's a number that's pretty close to it that we do know? 2. So I do know f of 2, and f of 2 would be 2 squared, which is 4. Okay, so kind of the idea of what's happening, we're going to draw a picture here, just a rough sketch. Oh, that's not good. Oh, it's looking worse. Okay, something like that. So we know this point for sure. That's the point 2. Now, the x value of 2.134, I mean, that's pretty close, like what, right there? So, use a different color. Its height is probably right a little bit up there. Okay. So, what we do is we go ahead and find the tangent line at a point that we do know that's pretty close. So, go ahead and draw in just a rough sketch of that tangent line. And although that's not going to give me the exact value, if I go to 2.134 on my tangent line, it's not going to give me the exact value, but would you agree that it's pretty close? So if I, for whatever reason, need to approximate this value by hand, I can use a tangent line to get us pretty close to it. Now, we want to get close. We want our x value to be pretty close to what we're looking for in the first place. Because if I did my tangent line, let's say at like 1, obviously that's not going to be as good of an estimate as that one there, right? So we are choosing the value that's pretty close to it. Okay. I don't want that tangent line. All right. So let's go ahead and figure out what our equation of the tangent line is. What the equation of this green line is. So we're going to go ahead and figure out the equation of the tangent line. Okay, so point slope for y minus something equals slope times x minus something. What point am I working with here? What's the point that I do know? 2, 4. Good. So I'm going to go and write that out in the nice ordered pair format. Okay, so y minus 4 is x minus 2. And what is my slope of the tangent line? How do I find that? The derivative, right? Derivative gives me slope of the tangent line. So we just simply have to find our derivative at that point. Okay, so we can do that. I'm going to do this off the side. F prime of x is what? 2x. Alright, so we want to know our derivative specifically at 2, which would be 2 times 2. Which is 4. Okay, so I have that my slope of the tangent line is 4. Okay, so again, this came from my derivative, and these just came from that point. So this is my equation of that tangent line, that green line that's pretty close to what we want, but not quite exact. Okay, now normally we want to simplify to make our lives easier. For this, we actually don't want to simplify. Let's go ahead and solve it for y, but let's not simplify it. So are we good with this being our equation of the tangent line? Okay. So that's my equation of the tangent line. Now let's go ahead and use this to get an approximate value at 2.134. Alright, so let's go ahead and do this at 2.134. So that would be 4 times 2.134 minus 2 plus 4. And you can see now why it was to our advantage not to simplify that. Because it's probably going to be a lot easier to do this math here. What's 2.134 minus 2? Good. 0.134. Plus 4. And you know, we have to multiply by decimal, but this actually isn't too bad. So 4 times 4 is 16, carry the 1. 4 times 3 is 12, plus 1 is 13, carry the 1. 4 times 1 is 4, plus 1 is 5. 4. And so we get that our approximate value would be 4.536. So that's the actual value on the tangent line. This height here is actually 4.536. But that's going to be our approximation for what's the value on our curve of f of x. So we use this and say, hey, I don't know exactly what it is, but I have a pretty good idea that the height for 2.134 is probably going to be, use the squiggle because it's approximate, it's probably going to be 4.536. I know that's not exactly what it is, but that should be decently close. So those that do have a calculator with them, just go and get it out real quick. Go and type in what is 2.134 quantities.
This is called linearization because we're using the line to approximate a value.
Yeah, we're using the tangent line to approximate. Line approximation, linearization? I'm not sure. Alright, what did we get for the actual number? 4.554. Pretty close, right? Not too far off. Now, in terms of calculus, is 2.134 super close to 2? Or just kind of close? Kind of close. In terms of calculus, we can definitely get a lot closer, right? Probably a better number would be like, if our starting number was 2.001 and we used 2, then that would be super close. But even with it being decently close, we still got for our answer to be pretty close as well. Alright, so this is the idea of what we're going to be doing. This is the idea of what linear approximation is. Linear approximation says, hey, I don't know the actual height here, but I can use a tangent line of a point very close to it to get an idea, a pretty close estimate of what it's going to be. Now notice here with our curve, my tangent line ended up being just under the curve, right? So my tangent line is probably going to give me a value that's less than the actual value, or an underestimation. And if I compare my approximation to the actual, did we get that it was an underestimation? Okay. So we'll talk about that more in just a moment. But notice my tangent line is under the curve, so it gave us an underapproximation or underestimation. Questions on this and kind of what the big idea is of it. So this is we're learning 2 topics today. This and L'Hopital's rule, and so this is kind of the big idea with linear approximation. Linearization. Okay. Okay, so let's actually write out linearization. We'll use linearization, it's less letters. Alright, so linearization, this is what we do. We are going to find a tangent line. We're going to find a tangent line to a function, and we'll just say it's f of x. At a point, we'll just say a point A, and then use the tangent line to approximate, and again, we're not getting the exact value, we're approximate, so squiggles are a big thing here. To approximate f of x for a value close to a. Alright, so we have a function, we have a point, and we can use the tangent line to get a general idea or approximate value for x values close to that starting. So again, that's what we did on that first page. We first said, okay, we need to know it at 2.134. Well, we know 2, pretty close to it, and we know that value. So we found our tangent line. We had to first find what the y value was with it, and found our derivative, the slope for it. Created that tangent line equation, then used that to get an approximate height for the one we were actually wanting to know. Okay, so just real quick, let's go ahead and take a look at, depending on the type of graph, whether we're going to have an over or underestimation. Alright, so let's see, let's go here. Alright, so we've got some crazy curve here, and let's go and put point A there. B over here. C. D. And why not have an E? Alright, so let's just take a look look at how our tangent lines relate to these. Go ahead and just draw in a rough little sketch of your tangent line for these. At each of the points. So you can draw in your little tangent lines on your paper. Okay, so let's go take a look at each of these. At point A, is my tangent line going to give me an overestimation or an underestimation? So anything on my tangent line, is that going to be higher than the actual or lower? Higher. We're going to have it as an overestimation here. If I take this point, here compared to the actual, it's going to be a little bit higher than that. So we have that ends up being over. How about B, over or under? Also known as over. All right, C, over or under? Under. Known as under. All right, how about D? Okay, you gotta do that one. Dunder Mifflin. All right, and E? Which starts to look like Eeyore, but it's not fun. Okay, so we have A is over, B is over, C is under, D is under, E is over. And this is kind of similar to our x squared graph. For C and D, our tangent line is below the graph, it's under the graph. So it ends up being an underestimation.
Is there ever a time where you have the closest, easiest point is so far away that your tangent line goes the opposite direction? So if you go up, it's over. If you move that way, it's under.
Great question. So what we're going to talk about here in a moment. Hold that thought. Okay, so what do you notice about the graph, characteristic about the graph, that seems to relate to whether it's over versus whether it's under? Take a look at the graph. What can we say? This is a hard, fast rule. If the graph is this, then it's over. If it's this, then it's under.
Over the y value and under the y value.
Good. If it's over our y value, the tangent line will be higher. Good. What else? Concavity. Would you guys agree that for this portion here, it is concave down, right? And we have then our tangent line ends up being above it. For this piece here where C falls along it, that's concave up. So our tangent line falls below it, so it's an under. Same with D. This piece here is concave up. So our tangent line falls below, so it's under. And for E, we're now at concave down. So our tangent line is above it, it's over. So our concavity actually indicates whether the tangent line will be above or below. So if our function is concave up, at the point of question, then using linearization will result in an underestimate. So if my function is concave up at that point, then the tangent line essentially falls underneath it, as we can see with C and D, and thus we have an underestimate. So for example, concave up, tangent line is underneath, and we can see all of our tangent lines are underneath. So this ends up being an under. For our specific example, that was for what, C and D? So for that example, though, we can see and then vice versa. If f of x is concave down, at x equals it, the pending question. Then using linearization. Linearization will result in an overestimate. And again, if we stop and think about that, concave down, all my little tangent lines are going to be above it. So we have that it's A. And for our example here, that was A, B, and E. Great question. So that's what I'm going to tie back in with Amelia's question. So at what point is a function either concave up nor concave down? A point of inflection. So at a point of inflection, then we won't be able to know exactly whether it is that over or underestimate, because we don't have whether it is specifically concave up or concave down. So that could be an example where you might have it's an over on one side and an under on the other. So now let's just recap. Oh, gee, our justifications come back once again. How do I know if a function is concave up? I like worded that you're like, well, let me tell you. Our second derivative must be what? Must be concave up. Positive, good, greater than 0. And for concave down, our second derivative must be less than 0. And at a point of inflection, it is 0, neither concave up nor concave down, so we wouldn't know for that. Right. Questions on that? Okay, so let's go ahead and do a formal problem with this type of problem you can see. Again, it's going to be very similar to what we did here, but we'll go something a little more extreme, a little more exciting. Need another picture. All right. Alright, so let's say we have 5x to the 4th, so our function is 5x to the 4th minus 12x cubed plus 16x squared minus x plus 1. So that's our function. That's not something fun to do by hand when we have decimals. Alright, so use linear approximation or linearization to estimate f of, let's go with just 1.01. So use linear approximation to estimate f of 1.01. Now again, if I were to take 1.01 and put it into this, that would be quite a bit of work to have to do by hand find the actual value. And they even prompt us by saying use linear approximation. Okay, so what's a number close to 1.01 that would be a good candidate for us? 1. 1, how nice! I love putting 1s in polynomials because it makes it so much nicer. Okay, so let's go ahead and use x equal to 1 to approximate. Alright, so again, we want to find our tangent line, and then use a tangent line to approximate that value. So for the tangent line, we need both the point and the slope. So if I use x equal to 1, then what is my y value going to be? How do I find my y value? Yeah, plug in. I need to know where on my graph this occurs. So I need to find f of 1. And so we get 5 minus 12 plus 16 minus 1 plus 1. What do we get when we simplify that? I agree with that. Alright, so f of 1 is 9. Alright, so we want to make the equation okay now. We've got the point. Now we need the slope. So what do I have to do for the slope again? Derivative. Oh, looky there. We can do the derivative of this, just a polynomial. 20x cubed minus 36x squared plus 32. I've got my derivative. Now what? Why did I want my derivative?
Equal to 0.
Not equal to 0. What was my derivative for?
Find the slope.
To find the slope. Where do I want to find the slope of? At 1, right? We're just trying to find the equation of the tangent line at 1, so we're just going to simply find the slope at 1. 20 minus 36 plus 32 minus 1. We'll get that. 15, we're good with that? So what was that we just found? Good, this is slope of the tangent line. Okay, so now we can go and write our equation of the tangent line. So I have y minus 9 equals my slope, 15, times x minus 1. Alright, so this is my tangent line I'm going to use to approximate. Are we good so far? Questions? Okay. Again, let's go ahead and write this. Where it's solved for y. And we won't simplify. Alright, now the only thing that is going to be different here. So this is my equation of the tangent line. And you'll see this if you look at textbooks or certain people do this when they, like if you look at videos online. They'll use the notation, they'll say L of x equals what we just found. So this red is my equation of the tangent line at x equal to 1, tangent to the graph of x. By using the L of x, what this indicates is, hey, this is the equation that I'm going to use to approximate. This is the linear approximation equation that I use. So it's just simply changing the notation to indicate this is a linear approximation. Not really necessary for you to do that, but that's what that means. Okay, so now we have the equation to use to approximate it, so what do? We're ready to approximate. How do we approximate? Yeah, we want to approximate at 1.01, so let's go ahead and actually do our approximation at 1.01. 15 times 1.01. Again, it's to our advantage to not simplify before, so we can see now. So we get 0.01 there. What's 15 times 0.01? We have 0.15. So 15 times 1 is just 15. Decimal move 2 places, so 0.15. It's 9. Okay, so now just to round it out, let's go ahead and present a nice orderly fashion because it said to estimate f of 1.01. So I want to say f of 1.01 is approximately 9. Alright, so again, we took our equation, we picked a point close to the one that we had to find. We said, hey, 1's pretty close. We found our point for it, so x and y. Found our derivative at that point, so we could write the equation of the tangent line in red here. And then we use the equation of the tangent line to find the approximate value, y value, that's associated with 1.01. And that is our approximation. You do want to make sure you always finish in the end to write it out. What do they do? You want to make sure that you do finish it out where you say, hey, the function value at 1.01 is approximately 9.15. Make sure you use proper notation. They ask for that, so answer that. Questions with that?
Is it like a previous function you have to do like this squiggly line equal sign every time?
So
Or just have like the bottom part of
that's a good question. You're fine with it just here because what we're saying is, hey, y equals this, because this is the actual tangent line. Sometimes you'll see the linear approximation. People will use this because it's saying we're approximating that value. But honestly, it's not something we're huge sticklers on. Definitely use it here, but other questions with this? Feels like we're back in September. It's really boring. Yeah, we're going to open the window. It's wintertime and we're opening windows.
Yeah, that's not cold outside that much.
It's because you guys come in and then the heat just keeps rising. Alright. So that's it for our... You got it? Yeah.
Yes.
You're in the front. You'll be fine. You're near the projector. It produces heat. Okay, so that's it for linearization. Let's go ahead and now transition to L'Hopital's rule, which I'm very excited for because I think it's such a fun rule. And you guys will like L'Hopital because it's a shortcut for certain limits. And I know you're thinking to yourself, how dare you, Mrs. Margraf, you withheld this shortcut from us all year. It's because it required the knowledge of derivatives. So I couldn't do it for you back in September because you didn't know derivatives back in September. Not necessarily. I know that one seems weird. Alright, go ahead and read that blurb at the top. Alright, so L'Hopital, like I said, I believe he was a French guy, pretty important French guy, and he came up with this shortcut, or discovered this shortcut for certain limits that we encounter. And like I said, I've seen where it's with an S as well, so not El Hospital, but L'Hopital. Alright, so we've talked about indeterminate form before. And this is where when you do direct substitution, you don't get a straightforward answer. And sometimes it requires us to do more work where we had to consider end behavior model. Sometimes we had to just consider, all right, which function grew faster than the other. Sometimes we might have to think about it further and decide, was there even a limit value? Is there a limit or does the limit not exist? Now, L'Hopital discovered that when we have limits that after direct substitution end up as 0 over 0 or infinity over infinity, then we can take this shortcut here, which is L'Hopital's rule, okay? So anytime that we have, when we substitute directly into our equation, 0 over 0 or infinity over infinity, then we can do the following. So this is what it says. L'Hopital's rule states that if the limit, when we do direct substitution, is 0 over 0, infinity over infinity, then what we can do is actually take the derivative of the top function, the derivative of the bottom function, and then evaluate the limit. So the limit of f of x over g of x, if it gives us the indeterminate form in this format, I can instead say, hey, that's equal to limit of the derivative of the top over the derivative of the bottom. No.
What about all those other forms on the top?
That you just have to do extra investigation. We don't have a shortcut for those. But these are examples of indeterminate forms. These ones, L'Hopital gave us a nice way to do it. Okay, now notice we're saying that the limits are equal, not the functions themselves are equal. Okay, so f of x over g of x is not necessarily equal to its derivative over its derivative. But the limits are equal. The value that it's approaching is equal. Just pretty interesting. Now, notice that in this here, so I started off, okay, I'm doing too many boxes of the same color. we started off with this. And L'Hopital's rule says you simply take the derivative of the top and then individually take the derivative of the bottom and do the limit of that. Did I take the derivative of f of x over g of x to get that? No, because what would I have had to do if I was doing the derivative of that whole thing? The quotient rule, right. So please, please, please don't take something easy like L'Hopital and make it harder and thus get the wrong answer because you're doing quotient rule. We're not doing quotient rule. L'Hopital did not say, hey, if you do the derivative of this quotient, then you can do the limit of it. He just simply said, take the derivative of f of x, individually take the derivative of g of x, then do your limit. Now again, it must be in this format in order to use L'Hopital. And in fact, I've heard from a couple different people that you must show on the AP exam that it equals 0 over 0, or pi, I keep wanting to say pi over pi, infinity over infinity in order to use L'Hopital. If you use L'Hopital without first showing that, then they don't like that. Okay? So always, as we always should do, check direct substitution first. Right, that we get the indeterminate form, and then we can do it. Alright, so here's a couple just simple ones. So we look here. If I take 2 and put it in, we have to do some algebra. 2 squared is 4, times 3 is 12. Correct me if I do any of my math wrong. 2 times 7 is negative 14, plus 2, that's 0. Do you guys agree that that's 0, 0? Okay. So we get that indeterminate form 0, 0. So this is equal to the limit as x approaches 2, because I haven't evaluated the limit yet, so I still need my limit notation. It's equal to derivative of the top. What's the derivative of that this top function here?
6 minus 7.
Good. 6x minus 7. And what is the derivative of my bottom function? 1. Oh, how nice is that? Okay. So now let's try doing this limit. If I take 2 and substitute it in, we get 12 minus 7. So 5. Notice I did not need to write my limit notation here because I'm now evaluating it by doing that direct substitution. A lot simpler than going through factoring this, reducing, and then doing the limit, right? That's what we had to do before. Questions with that? Now, again with notation, I've seen some books that they'll do something like this, where they say an H over top indicating this is, you're using L'Hopital's rule. I think I've seen also people just do like H or something like that to indicate you're doing L'Hopital's rule. I've been told that that is not required to say that those are just keys. Alright, so let's go take a look at number 2. What would we have had to do before to get rid of that radical? Possibly that conjugate. Remember how much work that was? Okay, well first let's see, can we use L'Hopital? So if I take negative 3 and put it in, I get 0. Negative 3 squared is 9, minus 5 is 4, square root of 4 is 2, 2 minus 2 is 0. Never in your life have you been so excited to get indeterminate form. Okay, so let's go ahead and do L'Hopital's rule. So again, this guy, we still have our limit notation. Derivative of the top is what? 1. Alright, go ahead and do the derivative of the bottom form. Did we get that for our derivative of the bottom? Got the chain rule piece in there? Very good, very good. Okay, let's go and clean this up a little bit. So I haven't done my limit yet, so I'm going to write my limit notation still. Alright, let's see. Immediately 1/2 and 2 reduce. That square root goes to the top. Does my x go to the top or stay in the bottom? Good, it stays in the bottom. It does not have a negative exponent. Are you guys okay with that? Okay, so now let's go ahead and try our direct substitution. I take negative 3 and put it in. I get 3 squared is 9 minus 5 is 4. Or negative 3, which is just negative 2/3. Look at how much less we have. Because you didn't know how to do derivatives when we did limits. Okay, some of you guys knew some derivatives when we did limits, but not everyone. Alright, now I want you to be careful. Don't get L'Hopital happy. You have to make sure that it is in the indeterminate form 0/0 or infinity over infinity before using it. So don't automatically assume. Always, always, always do direct substitution first, regardless of what limit you have. But if you get in this form, go crazy with L'Hopital. Alright. So note, it only works if it's in the indeterminate form. So like for this one, if I were to do direct substitution, I would get 7/2. And if you try doing L'Hopital, which means we can't do L'Hopital, right? It's not indeterminate form. And if you try to do L'Hopital, you would have gotten answer 2. So you can see it does not work unless it's in an indeterminate form. Okay, so let's go and take a look at another type of L'Hopital, in which it actually requires us to use L'Hopital again and again and again and again. So as long as your limit results in indeterminate form 0/0 or infinity over infinity, then I can use L'Hopital. If that result gives us an indeterminate form, then I can use L'Hopital again. As long as I keep getting 0/0 or infinity over infinity, I can do L'Hopital every single time. Alright. Let's go ahead and take, is that -2 there? Or is that positive? -2. -2. Okay. So again, first we must do direct substitution. For sake of time, I'm going to tell you it's 0/0. But do double check. You hate to get it wrong because it's just a number that it is. Alright, so using L'Hopital, the limit as x approaches -2. And our derivative of the top, 3x squared plus 2x minus 8. Derivative of the bottom, 3x squared plus 16x plus 20. Alright, let's go and try plugging in -2 here. What do we get on top when we substitute a -2? Are we sure it's 0? You're just guessing it's 0? It's a 0? Okay. How about the bottom? I hear some people hoping it's 0. Is it 0 or is it 28?
I was going to solve it.
It is 0.
No.
Don't automatically assume though when you get 0 on top that you're going to get a 0 on the bottom. You could have 0 over 20 and then that's just 0. Okay, so it's still in the form 0/0. We can use L'Hopital again. Woohoo!
Okay.
Alright, so again, we have not taken the limit. Don't lose your equal sign. So we get 6x plus 2 over 6x plus 16.
We're doing it again.
Yeah.
We can do that?
Because it's still in the form 0/0, we can do it again. Do we get 0/0 again?
No. I was going to say.
Okay. Alright, what do we get when we substitute in? Let's see, -12 plus 2. -12 plus 16. Did I do that right?
Yes.
Which of course is 2 over 16, right? Good. No, it's not 2 over 16. We can't just flash out the name, Charles. I can see if you're paying attention. So what did you guys say? 10 over -4, which is Can you imagine trying to factor those guys and reduce it from there? Or synthetic division? No, yeah, long division. Ugh, I don't think I want to do that. Okay, so same idea for number 4. Just every time you get an indeterminate form of 0/0 pi infinity over infinity, you can do L'Hopital. All right. let's take a look at 5 and 6. 5 we're going to write omit on for now because you don't know the derivative of natural log yet. But that's coming up soon. Once you learn that, you can do any type of calc B form you want. Okay, let's go take a look at number 6. Let's check. If I take 0 and put it in, I get 0 squared times sine of 0, which is 0, plus cosine of 0 is what? 1 minus 1. So we indeed get 0 over 0. Okay, let's go ahead and do our derivative. So L'Hopital, don't lose your equal sign, as I almost did. Alright, go ahead and do that derivative there. I know what it is, but I want to see if you guys know. Finish this out. See what you get. You guys try this. Alright, show me on your hand what's your answer, and if you need to use a negative sign, just use your finger and get a negative sign. What'd you get for your answer? Zeros? Good! Did anyone get -1? No one got -1? Alright, so let's take a look at our derivative here. What did we have to use for that top equation? Product rule. So second stage. You didn't do that, but you still got 0. Oh, okay. So second stage. Derivative of the first plus first stage. Derivative of the second. What's derivative sign? And then we have plus cosine x. What's the derivative of cosine x? Negative sine x. Negative sine x. And derivative -1? 0. Alright. So that's my derivative of the numerator. And what's my derivative of the denominator? 1.
Oh, right. I was going to say
Alright, so now let's go ahead and substitute away. So when we take 0 and put it in, sine of 0 is 0, which 2 times 0 is 0, so that first part's going to be 0. Take 0 and put it in, we get 0 squared times whatever that is going to be 0. And if I take 0 and put it in, we get minus, what sign of 0? 1. How many of you guys got scared when you saw that? Oh wait, what's my answer? It's just 0.
0 under. That's not under.
It's not under, so it's not under. Good. Questions with that one? Okay. So last but not least, let's take a look at this number 1 down here. Now, you can use L'Hopital's rule when you end up getting infinity over infinity, but honestly, what we did before is going to be easier with the end behavior model. So I could go take infinity and put it in, and I would end up getting, all right, well, this is going to control the top, this will control the bottom. So I get infinity over infinity. So then I could do my derivative, and then I get 6x squared on top and 6x squared on the bottom, and then I'm going to get infinity over infinity again, and I can do it again, and I get 12x over 12x, and then I get infinity over infinity again, and then I can do it again, and I finally get it down to my answer. So let's take a look at what we did before. When we do our end behavior, so we're looking at when x is approaching infinity, that means we only care what's happening on the ends of our graph. So that's what we want to consider top heavy, balanced, and bottom heavy. What type do I have here? Balanced, right?
Oh, balance.
I mean, I guess I could write that down. I have balanced, and what's the rule when my powers are the same? Yeah, it's just our coefficient. So I could actually get there faster without L'Hopital and say, hey, my answer's 2 cents.
What?
Well, that's what we did before, Bart,
Oh,
in case
yeah.
you forgot.
No, I forgot.
Okay, good. So just keep in mind, if we're looking at end behavior, it very well could be easier just to do our end behavior model that we did. Alright, questions with that? Okay. So your homework is to do worksheet 5.3. What we did was obviously note, so you have the back side of that, and then you have linearization practice.